In this video, we're going to talk about how to find the area between two curves. Now, before we begin this very first topic in Calc 2, you might want to refresh yourself on some of your Calc 1 knowledge. In particular, how to do an integral, in particular definite integrals, and how to do substitution for your integration. So if you need a refresher on any of your integration from Calc 1, take a look in the description below and I'll link to my Calc 1 videos where we go over indefinite integration, definite integration, and substitution with both types of integrals. And now let's move on to the Calc 2. We're going to consider the area S that lies between two curves. So consider the area S that lies between y equals f of x and y equals g of x. And also between the vertical lines x equals a and x equals b, where our functions f and g are continuous. And f of x is greater than or equal to g of x for all x in the interval a, b. So I'm going to draw a picture describing this situation. But basically, we just have two nice continuous functions. You know, you can draw those without lifting your pencil off the paper. And it's going to be sandwiched between two vertical lines. We're talking about the area in between these two functions. And we're specifying that one of the functions is always greater than or equal to the other one. That means we have a function on top and a function on the bottom. Let me draw this picture, and we're going to come up with a formula for how to calculate this area using all of the theory we learned in Calc 1 in developing our very first Calc 2 formula. So here's just a very generic picture explaining what's going on. Here's some function f, and I'll just make my g function like this. So my function f is greater than or equal to my function g. I'm going to say here's a, here's b. So this area that I'm talking about is this area in black. The area between the functions f and g, in between a and b. So it's just that section right there. And to figure out this area, what we're going to do is divide this region S up into n different strips, kind of like we did when we learned how to do just a definite integral of one function. So let's divide our S into strips. Let me just draw one generic strip here. So here's one particular strip that we're using, and we're dividing the whole thing up into strips. So we're going to divide that area S into n strips of equal width. And we're going to approximate that area of that strip of the ith strip, so of any of the strips, with a rectangle. With base delta x and height given by f of xi star minus g of xi star. And that xi star is just some particular x value in that little strip. So what I'm saying here, let me just draw this strip over on the side here, zoomed in. So our strip looks like this, sort of. This was our strip. We're saying that the width of the strip, we're calling that delta x, the change in our x values. And then we're going to pick some x value I'll just choose the middle point. And then the height of this rectangle that I'm using to approximate the strip, the height is equal to the top height minus the bottom. So up here we have f of xi star, and down here we have g of xi star. And the height is the difference between the two. So what we have now is we've estimated each of our strips with the area of a rectangle. And now what we're going to do, using inspiration from Calc 1, we're going to add all of the areas of those rectangles up. So then we can approximate the area of S with a Riemann sum. So our area is going to be approximately equal to a sum from 1 to n of the area of those rectangles. So f of xi star minus g of xi star times delta x. So we're adding up areas of all the rectangles. Now, if you remember back to when we first learned how to find the area beneath one curve, what we did from there is we figured out that the more rectangles you have, the better this estimation is. So we're going to define our area. The area between the two curves is equal to the limit as n approaches infinity of this Riemann sum. So we're approximating the area of this region by adding up the areas of a lot of different rectangles. And this limit is just saying we're going to have infinitely many rectangles that are infinitely thin. And when we add all of those up, we get the actual area. Now, if you're really strong in your Calc 1, you're going to recognize that the limit as n approaches infinity of a Riemann sum of this form is a definite integral. So we can rewrite this definition into the definition that we actually use in practice. The area in between the curves is equal to the definite integral from a to b of the bigger function minus the smaller function with respect to x. And this is our important formula for this video. That's how you find the area between the two curves. Notice the bounds of integration. We have our smaller value at the bottom, bigger value at the top like we're used to. And then it's always the bigger function minus the smaller function. So when we're integrating with respect to x, this is the top function minus the bottom function that goes into this integral. Let's do an example. Now that we've had all of the theory to set this up, show you that this formula actually comes from somewhere. Now let's actually do an example. Find the area of the region bounded above by y equals e to the x, below by y equals x, and on the sides by x equals 0 and 1. So the first thing I'm going to do is just draw a really rough sketch of what this is looking like. So here's 0, I'm going to say here's 1. 1, 2, 3. All right, so the line y equals x we know is a straight diagonal line. My graph is not to scale, but I would have a point at 0, 0 and a point at 1, 1, and I have just a nice straight line. And y equals e to the x, well, e to the 0 power is 1, and e to the first power is e, which is about 2.718. So I'm just approximating that. We know our e to the x function curves up like that. So the area that we're talking about in this problem is this region right here. We want to find the area of that region. And if you want a better looking picture, of course, use a graphing calculator or some other graphing utility to draw a better graph. Because quite frankly, I'm not always the best grapher, but I do well enough that I can tell which function's on the top and a general idea of what's going on. All right, so we need to set up our integral to figure out the area between these two curves. In order to set that up, we need to figure out which function is f in the formula, which is g, and what the bounds of integration are. Well, we know that it's supposed to be the top function minus the bottom function. And the top function in my picture is the e to the x function. So I have my top function minus my bottom function. E to the x minus x. We're integrating with respect to x. And now what are my bounds of integration? Well, they gave it to me, giving me where I'm bounded on the sides, 0 to 1. But in general, the bounds of integration are the smallest x value to the largest x value of the area that we're concerned about. So if I want to find the area between these two curves, I just have to do this definite integral. All right. All of that theory made it sound a lot more confusing, but handling this definite integral, we can do that. That's no problem. So the integral of e to the x minus x with respect to x. Well, first we need to find the antiderivative of e to the x. As you remember from Calc 1, the antiderivative of e to the x is itself. So I have e to the x. And then the antiderivative of this x, we have to use our power rule. Add 1 to the exponent and divide by your new exponent. You can also write that as 1/2 times x squared if you prefer that rather than dividing by 2. And now I need to draw my vertical line and my notation saying, hey, you need to plug in those numbers still. And then remember, with your definite integrals, our fundamental theorem of calculus says we plug in the top number first, then plug in the bottom number, and we subtract in between. So when I plug in the top number, I get e to the first power minus 1 squared over 2. And when I plug in the bottom number, I get e to the 0 minus 0 squared over 2. And I just have to simplify this, and that gives me the area in between my two curves. Well, e to the first power is e. 1 squared is 1. So I have e minus 1/2. And then I'm going to subtract e to the 0 is 1. And then this guy's just 0. So I have e minus 1/2 minus 1, which is the same thing as e minus 3/2. And I would leave my answer right there, unless you're told to round the answer. We know e is an irrational number, and unless you are told to round to a specific number of decimal places, you should leave your answers exact. I know that's tough to get used to. You're so used to coming up with a number as an answer. But this is the most accurate answer that we can give to this problem, rather than typing it in the calculator and rounding it. If we round it, it loses a tiny bit of accuracy. So this is what I would say is the best answer to this problem. E minus 3/2 is the area between those two curves. All right, well that wasn't too bad. Let's just do another couple examples just so that we get the hang of this. So the next example. Find the area of the region enclosed by y equals x squared and y equals 2x minus x squared. And so the first thing I should do is draw at least a very rough sketch. Doesn't have to be perfect. I know y equals x squared is just our standard parabola that touches at the origin like that. So this is y equals x squared. Now this y equals 2x minus x squared, the fact that I have a minus sign in front of the x squared tells me I'm opening downward. So we know that for sure. And then we can also find the vertex using our pre-calc skills. The vertex of this parabola ends up being at 1, 1. And it opens downwards. It looks something like this. It's not perfect, but something along these lines. And so the area that we're trying to find is just this little bitty area right here that's in between these two curves. And now let's just take a look at this for a second and think geometrically. If you take a look at this, if I were to find the area of this entire little red square here, that area would be 1, because over here is my point 1 and 1. So the area of this little red square I just enclosed this in is 1. That tells me that this green area that I want to find is going to be some fraction smaller than 1. So we can't really tell just by looking at the picture what it is, but when we figure out our integral and calculate it, if we got some answer like 5, we would know we messed up somewhere. Because this should be some number between 0 and 1. It's going to be some fraction. All right, well, let's try to figure this out. First, we need to figure out our bounds of integration and which function goes on top and which one goes on the bottom. And looking at our graph, you might think that, yeah, the bounds of integration are probably here at 0 to here at 1. If you want to be 100% sure that it is 0 and 1, all you have to do to find the bounds of integration is set the two equations equal to each other. That tells you the two places where these functions intersect, and that would correspond to those 2 points. So just to be extra safe, let's go ahead and solve this. If I add x squared to the other side and subtract 2x to the other side, I can then factor. And this first guy here tells me x equals 0, and the second guy tells me x equals 1. So that is corresponding to those 2 points, which is what we thought it was by looking at our rough sketch. But it's always nice to check just to be sure if it's not incredibly obvious what those intersection points are. So these are my bounds of integration, 0 and 1. So to set up to find the area between the two curves, we have an integral from 0 to 1. And now I need to write the top curve minus the bottom curve. Well, the top curve is the part corresponding to this top little arch of my green shape. That is on my upside down parabola. That's 2x minus x squared. So the top curve is 2x minus x squared. And then I have to subtract the bottom curve. The bottom curve is part of my opening up parabola. That's x squared. And then I integrate with respect to x. So if I calculate this integral, I'll have that area between the two curves. All right, so now let's just simplify this integral before we actually calculate it. I can combine some like terms together, and I get an integral from 0 to 1 of 2x minus 2x squared with respect to x. And now we're going to use our power rule to find the antiderivative. I'm going to add 1 to the exponent and then divide by that new exponent. So when I divide by the 2, it cancels out that other 2. And now on this guy, I get to add 1 to the exponent and divide by that new exponent. So I have x squared minus 2/3 x to the third as my antiderivative. And then I just have to evaluate this at 1 and at 0. Now take a look at this right now. When I plug the 0 in, This guy's going to be 0, and this guy's going to be 0. So I already know I'm subtracting 0 once I plug this stuff in. So really, my answer is going to be what I get when I plug in the 1. Plugging in the 1, I get 1 squared minus 2/3 times 1 to the 3rd, which is 1 minus 2/3, which is 1/3. Now remember that picture that I had up before. We knew the area was going to be a fraction between 0 and 1. An answer of 1/3 seems pretty reasonable with how our picture turned out too. So that might help you realize that, yeah, we probably did this right. It sort of matches my picture. That seems like a reasonable answer. So that's the area between those two curves. Now, to finish up this video, we're going to do one more example finding area between curves, but we're going to do something a little bit different with it. So, last example. Find the area enclosed by y equals x minus 1 and y squared equals 2x plus 6. And the graph is going to be given to you. So what this graph looks like, we have one straight line and then we have a sideways parabola. Looks something like this. So the area that we're talking about here is this whole region in between. Did we notice any sort of issues here? Remember, we were always saying it's going to be the bigger function minus the smaller function. And all we've done so far is do top function minus bottom function. The problem is, when I look at part of this integral, let me look just chopping off this piece. Over to the left of this vertical line that I just drew, the top function and the bottom function are both the parabola. And then it switches to be the parabola on top and the straight line on the bottom. That means we have to do two different integrals to do this, and that first one's a little complicated because we would have to, first of all, solve this for y, and we're going to get a plus or minus square root, and it gets to be kind of a mess. In situations like this, it's actually nice to integrate with respect to y rather than with respect to x. So if we're going to integrate with respect to y, the bigger function will be the function on the right. So it'll be right minus left. And when I look at this whole shaded region, the straight line is on the right and the curved parabola is on the left. So it's going to be line minus parabola, and then we just need the bounds of integration. Integrating with respect to y means we need the lowest y value and the highest y value. So I need the y values of those 2 points of intersection. Now, also, since we're going to integrate with respect to y, we need to solve both of our equations for x. So we write x as a function of y. So when I have y equals x minus 1, I can rearrange this to get x equals y plus 1. That's one of my functions as a function of y. That's the straight line. And for the other one, if I have y squared equals 2x plus 6, this is the same thing as x equals a 1/2 y squared minus 3. And you get that just by getting x by itself. So these are the equations of the same exact two curves, just solved for x instead of for y. So in order to set this stuff up, we are going to have an integral from some value to some value of the right function, y plus 1, minus the one on the left, 1/2 y squared minus 3. And I'm using a lot of parentheses just to make sure I get all of my signs correct. So that's the general idea. Right function minus left function, and we're going to integrate it from the lowest y value to the highest y value. So first, we need to find those y values, because from this graph right here, it's not clear what those y values are. To find those y values for our bounds, we have to set our two equations equal to each other. So let's find our bounds of integration. My two equations are y plus 1 and 1/2 y squared minus 3. And I'm going to solve this for y. I'm going to move everything over to the right side. That gives me a 1/2 y squared minus y and minus 4. And then I personally don't like this 1/2 in the front. It just makes it a little more complicated. So I'm going to multiply both sides of my equation by 2. 0 equals y squared minus 2y minus 8. This guy we can factor and figure out what y is. I'm just going to leave this integral up at the top because we're going to need that in just a sec. So if I continue solving this and factor, I'm going to get a y minus 4 and a y plus 2. So this tells me y is equal to 4 or negative 2. Those are my bounds of integration. So then it's just a matter of which one is A and which one is B. So let me take this integral that we had set up, and now we'll plug in our bounds of integration. Remember, the lower value is going to be your smaller y value. So that's going to be a negative 2. And then we go to the big y value of 4. And there's our integral to get the area between the two curves. So I would simplify within this integral before I integrate. So getting rid of all the parentheses inside, I get an integral from negative 2 to 4 of y plus 1 minus 1/2 y squared and plus 3, which if I rearrange inside of the integral, I have a negative 1/2 y squared, a positive y, and a positive 4. And now we're ready to use our power rule. So my power rule says that I'm going to add 1 to this exponent and divide by that new exponent. That makes that a negative 1/6 in the front. And then power rule says add 1 to that exponent and divide by the new exponent. And the antiderivative of 4 will be 4y. Then we just need to plug in our bounds of integration. So plugging in that 4 first, we get negative 1/6 times 4 to the third, which is 64, plus 1/2 times 4 squared, which is 16, plus 4 times 4. And then I have to subtract what I get when I plug in the negative 2. I have a negative 1/6, and negative 2 to the third is negative 8. Then plus 1/2, negative 2 squared is 4. And then I have a plus 4 times a negative 2. And now all that's left is just simplifying this. So what I get when I simplify, I get negative 32 over 3 plus 8 plus 16 minus 4/3 minus 2 and plus 8. Just be careful with your subtraction. Remember, we're subtracting everything in the second set of parentheses. You have to make sure you distribute that all the way through. Now, when I combine things together, I should get, let's see, negative 32/3 and a negative 4/3 makes negative 36/3, which is negative 12. And when I add all the numbers together that aren't fractions, I get 30. Negative 12 plus 30 is positive 18. So that area between those two curves was 18. Now, we did this one with respect to y. Would we have gotten a different answer with respect to x? Well, that's a good question, but the answer is no. It really doesn't matter. You can integrate these with respect to x or with respect to y. I personally choose whichever one it works out easiest for me. We did this one with respect to y because we were able to do it just as one integral, the right minus the left. If we had done it with respect to x, we would have had to split into two integrals. We had the part where the top and the bottom function were both part of the parabola, and then we had the part where the top function was the parabola and the bottom function was our straight line. We would have to have two different integrals doing top minus bottom, and the more integrals you have to do, the more complicated it gets. So would it be incorrect to do it with respect to x? No. But you would be causing a lot more work for yourself and you'd be much more likely to make a mistake. So that's all I have for you for this video. If you have any questions, you can feel free to drop them below. Or if you're one of my current students, you can also ask in office hours or email, and I'd be happy to answer any of the questions you have. Come back for our next video where instead of doing areas with our integration, we're going to learn how to do volumes with integration. So stay tuned. We're going to start working with some three-dimensional objects, and it's going to get pretty crazy pretty quick. I will see you in the next video.